Hi, my name is Luca Bez. I'm a postdoc with the Scientific Data Management Group here at Berkeley Lab. And I'll be sharing the work that we are doing towards understanding IO behavior with interactive exploration. So efficient data access is a huge challenge. We know that science teams from different domains work with tens and hundreds of terabytes of data on a daily basis. And we want applications to run fast. That includes doing I/O, input and output operations, which means reading and writing data. So how can we make our application, for instance, OpenPMD, Flash, or even a block cyclic-based application run its I/O faster, like 7 times faster, 4 times faster, or even 193 times faster? Well, first we need to understand what our application is actually doing in terms of input and output operations by visualizing and then trying to apply different optimization techniques that have been proposed over the last couple of years to improve performance. So the problem that we have is we normally are aware and familiar with the way that our data is represented at the application level. So we have different parallel and serial scientific applications, and we know that eventually everything that our application reads and writes will reach the file system and the storage devices. But there is a long way down between the application and the storage devices. And that's why we say that the HPC I/O stack is complex. We have multiple layers, and each one of these layers have different tunable parameters, different knobs we can turn, different optimization techniques that have been proposed for each one of these layers. So there is a lot of factors that could affect performance. So using all of this infrastructure in an efficient manner is a very tricky problem. But the first thing that we need to know and understand is, how is my application doing its I/O requests? How is my application reading and writing its data? So one way to understand what our application is doing is by using Darshan. Darshan is a popular tool to collect I/O profiling information. So what is an I/O profile? I/O profile is just a report that is going to aggregate some metrics and tell you where the time is being spent by your application, how much data has been transferred, what is the request sizes that you're normally using, so you can have an overall idea of what its behavior is. But okay, we have the data. I mean, is that enough for us to understand what can we do to make our application run faster and do I/O better? So we point out that there is a gap, so there are some missing dots between the profile information that we can capture and the different optimization techniques that have been proposed over the last years, where we can apply based on our workload and actually see performance benefits. So what we try to do here towards closing this gap is by using interactive exploration of different trace analysis to map the problems and the bottlenecks that we see on those visualizations into different optimization techniques, into different solutions that can help us optimize performance. So are we ready to explore? I mean, based on the thing that I said before, Darshan provides us with profiling, not with tracing information. So that's not actually true. Darshan can also provide fine-grained traces, which is not enabled by default. But what is an I/O trace? So the I/O trace will tell us which I/O operation is being done, what are the sizes of those operations, which rank issued it, when did it start, when did it end, and what interface was used. So if we get all of this information, we can visualize the behavior of the application and pinpoint possible bottlenecks and consequently apply some optimization techniques. The problem is that we don't have any tool to visualize or explore Darshan DXT traces. And the way that we can visualize by normally using static plots, we know that those have limitations, especially if we are trying to plot a lot of information, a lot of data. Imagine that for each read and write that your application is going to do, Darshan is going to capture that behavior with all of the information that I mentioned, like size, rank, start, an end. So how can we visualize that without losing context or losing information, which a static plot won't allow us to do to the basic pixel limitation that we have to show that. So the features that we're trying to seek here is to observe the different interfaces. So remember the stack there, we want to see how the calls, the IO calls, are translated from one level of the stack to a lower level, reaching the parallel file system. We want to be able to focus on specific periods of time or in a specific subset of ranks to observe their IO behavior, but also have contextual information. That is, what is the size, what is the interface, when did it start, to which server that request was sent to. And we also want to have different ways of focusing on operation, on size, and on speciality. So how those requests are distributed in the file. So we propose the DXT Explorer tool, which is a way of visualizing those traces in an interactive fashion. You can access the source code on GitHub or pull our Docker image. And some of the features that are available on DXT Explorer is to allow us, for instance, here to focus on specific periods of time. And for each one of the points that you're seeing here, they represent I/O operations on the different layers. On top, MPI/IO, on the bottom, POSIX. So you can see that even though we have some collective operations where all the ranks are doing some specific read or write calls, in the top you can see those big blue boxes, they are translated into smaller calls at the POSIX level. And some of those calls are actually taking a long time. You can see those here in red, which take a long time and delay the entire application. So we can visualize that looking at the traces. We can also see the data transfer sizes, the offset, the duration, and all of that contextual information in each one of these particular plots. We also know that I/O size impacts performance. Doing very small requests will harm our application, but also cause performance interference for other applications since we are using a shared storage file system. You can see on this particular transfer size plot on the DXT visualization an execution with an application that uses HTF5 to write data and metadata. And that is done after each one of the iterations. You can see that on each iteration we are actually writing a lot of data, but we do have the metadata being written by only a subset of the ranks instead of all of them, and it's a very small size. So we can use this to guide us and apply different optimization techniques that would be suitable if we can see this behavior in our application. So what are those common optimization techniques that we can apply? This is a non-exhaustive list, just some of them that we'll be using in the test cases that I'll be showing you later on. We have luster striping, collective I/O, HTF5 alignment, and HTF5 defer metadata flush. So what does this mean? For luster striping, we can recall that our file will be broken down into smaller chunks, into a predetermined stripe size, and those chunks, those stripes, will be sent to different servers. Based on the number of servers, we have the stripe count parameter. So we can adjust the stripe size to have larger requests, larger stripes, or smaller stripes, or even more parallelism if we have more servers. So those are some of the things that we can tune on one of the layers of the I/O stack. We can also have collective I/O operations that instead of each rank making its own request to the file, we can have a subset of them. Let's say rank 0 and rank 2 will aggregate, take all of the requests for the different ranks and issue larger and contiguous operations into the file. This is called collective I/O. We can also have HTF5 alignment. So remember that we have the stripe sizes, and if we want to access some information that is between, not well aligned with how the stripe, how the file is broken down, we'll have to make more requests and access some non-contiguous portion of the files. So if we set alignment so that our application will be aware of those boundaries, read and write operations will fit onto those stripes. We can also have the for metadata flush, which instead of writing the datasets throughout the application and then writing metadata, we just store the metadata in cache and write everything at once in the end, so improving performance in some cases. So let's see how we can apply these optimizations based on the traces and the things that we see from the DXT Explorer. The first test case that I'm going to show you here is the OpenPMD, where collective operations can help us gain performance. So if we look at the right side here, we have the left side, sorry, we have the execution time, all the different ranks, and the two interfaces, the MPIO and the POSIX. You can see that we have data and metadata being written 10 times throughout the execution of the application. One thing that we can see on the first glance looking at this plot is that both layers, the MPIO and POSIX, they look very much alike. So that's one indication that we're not using collective operations, not collective data operations, nor collective metadata. So the first optimization that we tried here was to enable collective operations. It's just a flag that we need to set on Romeo. And we got 1.54 times speed up. Then we tried to also enable collective operations for the metadata. And even though we said that, we discovered that the application was actually not using collective metadata calls. And that was due to an issue introduced in HTF5 1.10.5. So that helps us fix a problem in a library that's very commonly used. And when we combine all of these optimizations, on this particular execution in Summit, we got up to 6.8 times the performance. And you can see on the right side now how the same application looks. So we have still the 10 time steps there. They are very well behaved. The requests are aggregated, and you can see how much we gain in terms of performance. The other test case that we have here is the Flash application, where we can apply different HTF5 tuning that will also help us attain performance. So Flash writes 2 checkpoint files, which are over 2.3 terabyte each, and 2 plot files, which are approximately 14 gigabytes each. It's an execution on Summit, and we can see the same problem we have with collective operations. So the MPIO and POSIX look very much the same in our initial run. So when we attempted to turn on collective operations, we combined with setting the alignment in HTF5 and writing all the metadata into cache only at the end, so the defer metadata flush, we got up to 4.1 times improvements using those operations. And you can see from the plots here, at first glance, if I don't tell you that they are from the same application, you might think, oh, maybe they are different applications because the behavior we see is completely different. And those are some of the techniques that have been present for quite some time, like collective I/O alignment, or even the for metadata flush that we have available to us, but we need to know when to use them. And because we have all of those techniques, combining them is a difficult process. We can see here for the block cyclic application, this is one example on Cori, where we have write and read requests. Particularly for the write request, our baseline took over 8 hours to run. So we just stopped there and took the worst optimized scenario as the baseline. And you can see how we can apply different techniques like setting striping, striping plus alignment, or just using collective operations, collective with striping, or all of the three. And some of those optimizations, they can reduce the runtime up to 5 seconds. So that's 193 times the performance improvement. While in other scenarios, if we look at just the write operations, just using striping, correctly setting the striping size already gave us the best runtime. So it's a little bit harder to know when should we use each one of the optimization techniques, and our hope is that by using the DXT Explorer, we can visualize and see some indications of where the performance bottleneck is, what is the I/O problem, and how we can actually use the available techniques to improve performance. So DXT Explorer does add that interactive component analysis to the DXT trace analysis. It moves one step closer into connecting the dots that we have between the profiling and the tracing information that we have with all of the techniques that we have available. So we still need some research on how to better report that, but knowing that something is wrong is already the first step towards fixing the problem. So the tool is available for everyone that wants to use on their own traces. And what we plan to do now is find better ways to report that to end users. So for instance, if we have those small requests being detected by the plots, we can highlight and make some recommendations automatically on how to map the problems that we are showing the user into different tunnable options. Like if you have small requests, let's try using collective I/O if you're not using so. So these are the next steps in our research efforts. So how can I use that in Cori? I mean, that sounds very interesting. Let me know how I can use it. So Darshan is already loaded by default for all applications. There's nothing else you need to do about that. You just need to enable the DXT tracing module in your job. So in your job script file, you can just export DXT enable IO trace and set it to 1. You run a job, it will generate a Darshan file in a specific location in the system. You can find that more in the NERSC documentation. You download that trace and you can locally give it to the DXT Explorer tool and generate the interactive plots for operations, for transfer size, for spatiality, and give that first step towards optimizing your application. So it's our turn now. We hope this tool will be useful to you. If you have any questions, you can reach us. Remembering that we have a Docker image where you can pull the entire DXT Explorer tool for you to use. You can also access the source code and install it directly. For those who got interested and want to play around first, we prepared a demo, so you can access the bit.ly/DXT Explorer, where you can play with some example traces and see how the tool behaves when you use its different features. And I want to acknowledge that this is a work that we are doing in the context of the Exascale Computing Project, more specifically the XIO project. And it's a collaboration between all of these researchers from different labs that provided those applications with all of those different problems that we were able to provide some performance improvements by looking at the application's I/O behavior. So with this, I finished my presentation. I hope this has been useful. And if you have any questions, I'll be more than happy to answer them. So thank you very much.